start sharing the screen. And I have to apologize. My last class ran over, so I didn't get to click on this to open up to where we had left off, but I want to go back up to the top to chapter 13 notes. And I'm looking right now, everything is for chapter 13 is due on the 19th, which is Monday. And I'm looking at where we are. And I want to make sure that we have time to have a day to just answer questions. So would it hurt anybody's feelings if I changed those due dates to the 21st instead? So that chapter 13 will be due on Wednesday, the 21st, instead of Monday, the 19th. Is that all right?
Yes.
Okay. Then we were left off discussing some of the ideas of statistical inferences and sampling techniques. But before we go there, I think I promised at the beginning of the semester that I would start each class by asking if there was anything that anybody wanted to look at in any of the homework or the activities. And so before we pick up from where we left off with those ideas of sampling techniques, does anybody have any questions on anything at this point?
Can you go over number 18? I think it's on 679, but I'm not completely sure. It's on 678, the page number, but it could be the one over.
All right. Thank you for asking. Question number 18, did you say, huh?
Yes, please.
Okay. Okay, question 18 says collecting their own data actively engages students in the study of statistical notions, not only in heightening student interest, but also in a sense of meaning and reality to the study of statistics. So what they're saying there is, it's real easy to pick the examples from the textbook and use the numbers that are in the textbook, or just to provide numbers for kids to use for statistics. But sometimes it's more fun if they have ownership of the values. So, name 4 activities you deem particularly suitable for a class of elementary students that would involve the collection and representation of data. I mean, I don't ask you guys to collect data, but it's along the ideas that when we were looking at things like the mean, median, and mode, we used information about you. How many brothers or sisters do you have? Or what size shoe do you wear? Where I collected data from the class. And so if you were working with elementary students and you were looking at the idea of, let's say, mean or median or mode or anything like that, what might you do to have students collect data? And then once they collect it, how would you have them represent it? So be creative. Whoops, I didn't mean to hit that. I apologize. Be creative as you want. One example might be you might ask students, what would be something that you might ask students to count and measure? You might have them count, let's say, how many kids in the class are wearing sneakers today? And you might make a pie chart, the number of kids who are wearing sneakers as opposed to the number of kids who are wearing shoes. Or you might ask kids, I don't know, do you guys have any ideas that something you might have the kids measure even? You might have them measure their heights. And everybody, partner off and use a ruler to measure their heights. And then you might make a frequency distribution of the heights of the students in class, right?
I used their birth, like the month of their birthday.
Okay. And how would you represent that?
A dot plot.
A dot plot, great. But they ask you to not just do one, but come up with 4 activities.
That was one of the examples I used.
That's, yeah, and that's great. That's all that they're asking you to do. Be creative, come up with things that you think might, make the kids a little bit more interested than just a random set of numbers. All right,
Okay, thank you.
you're welcome. Anything else? If not, let's pick up from where we left off. And we had talked about biased sampling, and I think I was ranting and raving about self-selected sampling, where you decide if you get to participate or not, where you get to choose to participate. Is usually biased. And so in the handout for the notes, the next thing that I cut off was the idea of random sampling. It's usually the gold standard. It's not biased. And it's where every member of the population has an equal chance of being selected. Every member of the population has an equal chance of being selected. And so, for example, if I wanted to do a study of the student body at Niagara County Community College, and I decided that there were too many students for me to actually use, and so I want a random sample of, let's say, 200 students. And I want this to be so that every student has an equal chance of being selected. One way I could do it is I could make a printout of everybody's names, and I could cut them into little strips and put them into a big box and shake it and pull 200 names out. And that would be totally random. Instead, if I had a list of all of the names and I wanted 200 names, I might pick a random spot on the list, and then from there, take every 30th person until I got my 200 names. And that would not technically be random, but where I started and where you fall in the list, that would be pretty random way of selecting. And does it make sense that if we randomly picked people, we'd have a better chance of having a representative sample? Or to be, we could have like a striated sample where we might, I think the ads say that the college has something like 40 or 50 different programs. I could go through and I could pick, one person from each program and have that person selected randomly. And that might also be considered a random sample, and it would be unbiased because we'd be representing, fairly a cross section of the population. And this idea of random sampling, all right. In the last homework, there are some questions that just ask you, hey, is this random sampling? Is this a good technique? If I sampled in this way, do you think it's really representative or do you think it might be biased? All right, any questions on those ideas? Not hearing any. Let me just make sure I got all of those definitions from their preceding page. Yep. Then going on to that next page of notes. When we talk about a population, with a population, we consider the data to be our population. Let me make this a little bit bigger before I go on. Our population parameters is what we would call the data from the population. When I'm dealing with the whole population, we use different variables. In uppercase N would be the population size. This funny looking symbol is a Greek letter. It's the letter mu. And it's the population mean. And this is a lowercase sigma. We had used the uppercase sigma to mean total. A lowercase sigma is the symbol that's used for the population standard deviation. And again, most frequently, you don't have necessarily all of the data for the population. And so we use oh dear. I'm sorry, my stylus just decided to crap out on me. Let me see if I can get it to write. We use the sample to estimate the population. And with a population is called parameters. With a sample is called statistics. Lowercase n is the sample size. This X with a line over it is called X bar, and that's the sample mean. And S is the sample standard deviation. And so if you have an opportunity to take a statistics class, you'll find the relationship between these in the formulas that we use when we use that sample to estimate population. Recognize though, with population terminology, it's parameters. With sample, it's statistics. Uppercase N is the population size, lowercase n is your sample size. And when it comes to the mean and the standard deviation, for the population, we use those Greek letters, mu and sigma. But for the sample, we use X bar and S. I believe for most of what we'll be doing with the, beyond the statistics, we'll be looking at sample values more than population values. What's interesting is this thing that's called the normal distribution. It's called normal because a lot of real life data, almost most real life data, fits it. In order to be normal, what has to happen is that the mean, the median, pardon me, that's an N, sorry, and the mode are all about the same. So they're approximately equal. And so let's think about an example. Let's make pretend it's not a pandemic. And we're on campus. And I want to look at the heights of people on campus. And so I'm going to take everybody who's on campus on a given day. And I'm going to see how tall they are. I'm going to find the mean, the average height. And then to find the median, I might go through and line everybody up from shortest to tallest. And the median would be the middle of that line. And when I get to the middle of that line, if I took everybody in the college and lined them up from tallest to shortest, do you think the middle of that line would be pretty close to the average height, the mean? And don't you think that most people's height would be close to that middle, the mode, so that the mean, the median, and the mode are about the same? Does that make sense? When you look at any large group that you've ever been in, when people line up by height, isn't the middle of the line usually close to the average height, and aren't most people about the same height there? The other thing that has to happen is if the frequency decreases as you go away from the median or from the mean. So what does that mean? If I were to go to that line of people from shortest to tallest, I'm not a very tall person. I'm like 4'11". So I would be on the short side of that line. Do you think there'd be many people close to me in height, or do you think there'd be a lot fewer people my height or shorter? As we get away from the average height, we would expect the frequency to go down. One semester, I'm like 4'11". One semester, I had this basketball player in class. God bless his soul, he was 6'11". I couldn't talk to him if he was standing up. It was just too much of a difference. And if we look at that end, where the really tall people were, you wouldn't expect there to be many people at those heights either. And so when I get further away from the average, either a lot higher or a lot lower, you would expect there to be a smaller number of folks. The frequency would go down. And what happens is the frequency polygon is relatively symmetric. And we talked about the idea of symmetry, that if I folded it in half, the two sides should meet up. And way up here, one thing that I forgot to add that's important is we only use this reasoning if I have a large sample size. And so that frequency distribution, that frequency polygon, looks like what's called a bell curve. And so over here, my horizontal axis would be my data values. My vertical axis would be my frequency. Somewhere in the middle, I'd have my mean. It's in the middle, it would be the median. And because it's the mode, it would be the highest frequency. And as I go away, as I get smaller, I'd expect that frequency to go down. And as I get larger, I would expect that frequency to go down. And doesn't quite exactly match up if I fold it in half, but it's pretty gosh darn close. And so when you hear people talk about something like a bell curve, they're talking about a frequency polygon, pardon me, for a very large number. And because it's for a very large number of values, those straight lines will start looking like a curve. The mean should be in the middle, the median, and should be the highest point, the mode. And as I get values that go away, either on the smaller side or the larger side, I expect my frequency to decrease. There's something that's called the 68, 95, 99.7 rule. And what that says is that if data is normally distributed, and so again, normally distributed, it means I've got a lot of folks. The mean, median, and mode are about the same. And as I go away from the mean, my frequency decreases. And it's sort of symmetric. The first part says that 68% of the data fall within 1 standard deviation of the mean. The second part of that rule says that 95% of the data fall within 2 standard deviations of the mean. And the third part says that 99.7% of the data fall within 3 standard deviations of the mean. Okay, and before we go too much further, yes, you're right. This is not material that you would expect to cover with elementary students, nor the standard deviation. The authors of the textbook, pardon me, have homework questions as if you're discussing standard deviation with students, but I don't see that happening in an elementary classroom. What I do see happening in an elementary classroom with respect to this and where we're going next with the Z-scores is you as a teacher being able to look at data about your class and compare them to statewide population, national population, and understand how those comparisons work. Because this isn't something that you wouldn't really expect the kids to do, but this is something that you should understand in terms as the teacher, analyzing your students' data and explaining what it means to parents. This is a much more adult view. So let's look at, I'm going to insert a whole other page. Let's look at an example. The standardized test that I kind of know the mean and the standard deviation for is on the SAT exam. And have you folks heard of the SAT exam? Did any of you ever take the SAT exam, that college entrance exam? It's a standardized test. It's scaled so that the mean is 500 and the standard deviation is 100. And so if I look at that 68, 95, 99.7 rule, when I use this rule, I always draw my bell curve. I label the mean in the middle. So for this example, my mean is 500. And then I count out by the standard deviation. So here, my standard deviation was 100. So I'm going to count by hundreds: 500, 600, 700, 800. And in the other direction, 400, 300, 200. Now, that 68% rule said that within one standard deviation is 68% of the population. So I'll say that 68% score between 400 and 600. So 68%, that's approximately 2/3. So about 2/3 of the people who took that test would have scores between 400 and 600. Then 2 standard deviations away, that would be going 2 away on either side. Between 300 and 700, that's my middle part, my 95%. So I'd say that 95% score between 300 and 700. 95% is almost everybody. We'd expect most people to get their scores on any section of the SAT exam to be somewhere between 300 and 700. Then lastly, 3 standard deviations away. Well, 3 away from 500, 1, 2, 3 would be between 200 and 800, and that's 99.7%, or almost everybody. So 99.7% score between 200 and 800. And so if you're looking at a student scores and you're comparing them to, let's say, statewide results on a standardized test, you'll be given the mean and the standard deviation. And when you're meeting with mom and dad and they tell you, well, Johnny scored 550, what does that mean? You can say, well, they're in the middle, 68%. They're above the mean. As opposed to if they said Johnny scored 250. 250, their score is low. You might think of sending them for extra help or, whatever remediation there is. But having this, can you guys kind of sort of wrap your minds around what this 68, 95, 99.7% rule says? Any questions? Can you guys hear me?
I don't have any questions.
Okay, great. Did any of you ever see any of this in a high school algebra class or a high school statistics class?
We were supposed to finish statistics after mean, median, and mode, but then COVID hit, and we didn't start anything new after COVID hit.
Okay, all right. I'm thinking way back a million years ago when I was at Canisius College and I was getting my bachelor's in education. I was getting my bachelor's in secondary education, and there was a class that was required for math for secondary education majors, and the lion's share of it was looking at the standard deviation, finding the standard deviation back in the day when we didn't have a calculator, so all the computation was done by hand. It was a lot more involved, and there was a lot spent on this part because it was important as a teacher to be able to use it to interpret your results. So then the next thing that we're going to look at is percent time. Has anybody ever heard of the percent time? The percentile is the percent of the population less than or equal to the data value. So for example, if I score at the 50th percentile, it doesn't mean I got a 50 on my test. It doesn't mean I only got half of them right. It means I did better than half of the people who took the test. It means my score was right in the middle. I know that when my children were young and we took them to the pediatrician, they would measure their height and their weight. And they would always tell us that, the child, my kids, so they're not, whatever, would always be at the 25th percentile for height. And to say that they were at the 25th percentile for height meant that they were taller than 25% of the kids their age, which, other side of things, meant they were shorter than 75% of the kids their age. And so that idea, have any of you ever received information in terms of not an actual raw score, but a percentile? Usually if we look at that SAT exam, I know that a lot of times those results are given, you're given the raw score, but you're also given the percentile. And so on the SAT exam, if you scored a 500, you're at the 50th percentile. You did right smack dab in the middle. Instead, let's say you did really good in the SAT exam and you scored at the 95th percentile. Well, that means you scored better than 95% of the other people that took that test. You top-notch student. If I look for a percentile from a sample, I actually just go through and I find the percent of the sample at or below that value. And so give me just a second. I'm going to go back and pull up some data that we had taken out of class when we were first starting looking at statistics. let's say, for example, we had, I'm looking for something, shoe sizes of class. And they were in order 5, 6, 4 people had a 7, 2 people had an 8, 1 person had a 9, and 2 people had a 10. If I ask, what's the percentile of size 8? Well, if I look here in my sample, we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 people. If I ask how many are 8 or smaller, that's 1, 2, 3, 4, 5, 6, 7, 8. And so the percentile for 8 is we had 8 people out of 11. And so if I take 8 and divide it by 11, and again, in this section of the chapter, I said the other day, you should feel comfortable using a calculator, because again, this is computation you would do with as an adult with parents and not with the kids. That would give me, it gave me about 0.73. And so that would be 73%. So we'd be at the 73rd percentile. What if I ask you to find the percentile of size 6? How many people were a size 6 or smaller? Six or smaller is 2 out of my 11. And so when I take that 2 and divide it by 11, I get 0.1818 repeating. So I'd say that that's 18% or the 18th percentile.
Why was it 2/11 when there's 1 6?
Because it's 6 or lower. For
Oh,
size
okay.
8, we were looking at how many were 8 or smaller.
Oh, okay. Thank you.
Okay, so it's the number of people at or below that level. So if I go back to that example of the SAT exam, I took my SAT exam and I got my score and they reported the percentile. When they reported that percentile, do you think that they actually physically went and lined up all of the papers of people who took the test that day and counted how many were below my score to find the percentage? No, they used the normal distribution in something called the Z-score. And the Z-score can be used to find the percentile from a normal population. It's a measure of standard deviations from the mean. And you can see the formula there. Z is equal to X minus X bar over S. which is the data value, minus X bar is the mean. And that difference divided by the standard deviation. And once we have a z-score, we're going to use a table to find a percentile. So let's look, for example, at the SAT English part of the test, where the mean is 500 and the standard deviation is 100. And I want to find the percentile for a score of, let's say we've got a score of 675. The first thing that I'm going to do is find the z-score, which again is the value minus the mean over the standard deviation. So we'd say that the z-score for 650, sometimes you see that little subscript written there. That tells you what number you're finding the z-score for, is equal to that number, 650, minus the mean. I'm sorry, it wasn't 650. It was 675. I apologize. Would be that 675 minus the standard deviation divided by, I'm sorry, minus the mean, the value minus the mean divided by the standard deviation. Let's try that again. The z-score for 675 is the data value 675 minus the mean 500 divided by the standard deviation 100. So that would give me 175 divided by 100, which would be 1.75. And so my z-score is 1.75. To find the percentile, I'm going to use a table. For you folks, that table is in your textbook. It's in the textbook. Let's go to contents. Here we are. Chapter 13. It is at the end of the chapter. I think it's right near the chapter summary. I have to apologize. I should have looked up in my textbook and written down the page number. So that here we have the negative half of the table on page 718. But our z-score was positive, so I'm going to look at the part of the table on page 719. And we had said that our z-score was 1.75. And so the first two digits is 1.7. So I'll go over here to the row for 1.7. The last digit is 5. So I'm going to go to the column for 0.05. And you see they overlap at 0.9599. Can everybody see that?
Mm-hmm.
And so that tells me that that score of 675, we're going to change that into a decimal. That's 95.99%. And so that would be saying that that score of 675 was at the 95.99 percentile, or if you got a 675 on that English, you did better than 95.99% of the people who took that English test. And so from the table, we get 95.99 percentile. And so this is where, if you gave a standardized test, I'm thinking back when my kids were in elementary school, one of the standardized tests that they always took was the California Achievement Test. And the teacher had the raw score. If the teacher had the mean and the standard deviation, they could find the percentile of my child, and it would tell me where my child stood next to everybody else in the country that took the test. Again, you don't want to define kids by numbers, but you see how being able to interpret these results and use them is a useful tool, especially if you're a teacher. So that gives me the percent below. If I want to find the percent above the score, so we had the Z-score for 650. I'm sorry, why do I keep saying 650 when we chose 675? Was 175. So that 675 was at the 95.99 percentile. Well, if I want to know how many people scored above, the percent above 675 would be equal to that 100% minus that 95.99%. So we'd say that only 4.01% scored better than 650. And I'm looking at the clock, and the clock is saying it's that time. So I'm going to stop here. But before I do, does that make sense that if 95.99% were below me, I'd subtract from 100 to find the percent that's above me? Because the whole population would be that 100%. I'm going to stop sharing, stop recording for all intents and purposes,